Okay, so this is going to be 12.6, the normal distribution. Again, this is probably something you've heard of before. So basically the normal distribution is a continuous random variable that has a normal distribution if for some mu and sigma that has to be greater than 0, so we can have a negative one, the random variable has the following density function. So this is basically the PDF of this continuous random variable, but the normal distribution is special. So if x is normally distributed with the mean and variance, this is how you will always see it written. So it wouldn't necessarily have the mu and sigma there. It would actually have values, so it might be like 0 and 1, whatever. It could be any numbers. So also it can be shown for our random variable that the mean is mu and that the variance is sigma squared. So basically it's x normal distribution of mean comma variance. And it's symmetric about the mean. So for figure 2, this is an example of a few different normal distributions, but if you notice, they always are symmetric on both sides. So this is really cool and it's helpful when we're solving, and that's why the normal distribution is so popular. But these are some properties. Basically, if we have a normal distribution, then if we have a constant in front of our variables, so if we had like 4x, we just put 4 in for both of those, but you have to square it right here. And then for the next one, it's kind of the same idea, except you just add your constant in to mu. And then the last one's the trickiest. So basically, if we have two different variables, they're independent, they would have their own mean and variance both times. So then if you add them together, basically it's just going to be adding the means and the variances together. So these are pretty, not self-explanatory, but they make sense. They're not tricky properties. So finding normal probabilities via standardization. So sometimes we're going to have to standardize variables. So if we have a random variable z, 0, 1, sorry about this with all the parentheses. I don't know why they were left off in like all of mine. So we call this a standardized normal one because it has a mean of 0 and a variance of 1. So that's like the most standard you always see. In your textbook, there is a huge table. I didn't put it in the notes because it's like 2 pages long, and that is the densities. They've computed multiple densities for the standard normal distribution. So it is a like standard general across the board for the standardized one, 0 to 1. And that's because if you remember up here, it would be symmetric. So if the mean is 0, that means it's negative 0.5 one way, and it would be 0.5 the other way. So the computed densities would be right here. The random variable has to be less than or equal to the value you are computing for. So for example, if I want to know if I have the probability of the random variable is equal to -1 or less than, you'd plug it into f or whatever it is in the table. So if I went and found -1 on the table, it would yield this probability. You don't even have to compute it. But that is only for the standardized normal. And then standardization is actually the procedure we use to find the probabilities of any normal random variable. So, and it's not just this one. Okay, this should say, suppose, I'm sorry about that. Suppose x is a normal variable, and we want to find some valid or some probability in this interval. This is how we would standardize it. So if you notice, you're just plugging in the values here. So if you have the mean and the variance, this is pretty easy. You just have to follow this formula to standardize it. And we'll do this in one of our examples. The central limit theorem is basically, if I have all these random variables and n is sufficiently large, so like a really big number, The random variable x is if I add all these up to the whole random variable, I can actually approximate it by x hash mark. And so it follows that for like the mean and variance. Basically, it's just them all added together, approximated. So when we say that it closely approximates x, it's basically just the same thing that we write before. So we can actually find these probabilities with Excel, and I will show you. So we'll do some problems at the end, and I'm going to have like a separate clip of me screen recording in Excel how to do it. But it's not super involved. It's basically just using functions in Excel. Probabilities involving a standard normal variable, so the standardized one we talked about before with 0 and 1. You can use the norm dist function in Excel. So if I put in -1, it would give me out that same 1.587. I guess it could be more useful than looking it up in the table. So like, let's say you're in Excel, you're doing a bunch of work. Maybe you just need to know this for whatever problem you're doing. You could just have it spit it back out to you instead of going into your textbook and reading the whole table. So it also can it could be for any normal random variable. That was just, I was saying that so we could check our work. But so if you have a normal random variable, if you enter this formula, it's going to return the probability that it's less than a, or of that interval. So you notice it always has to have 1 here. We always have to have our variable. So this is kind of like the interval a to 1 because we can't have it be bigger than 1. And you have your mean and your variance, or yes. So suppose we want to find the pth percentile of a normal random variable, which would just be a decimal, but using our mean and standard deviation, we simply just have to enter the formula into Excel, norm_inv, and you just have to have p, your mean, and your standard deviation. The p would be for when we're looking at confidence intervals, I believe, like 95% confidence and stuff like that, and it's going to just return the probability of that percentile. Okay, so this will make a lot more sense now with the problems, but it says see video for solving with Excel demonstration. So I'm going to go through and set these up, and then at the end of this video, there'll be a clip of me doing it in Excel, just actually running the formulas. So the daily demand for milk in gallons at Gillis Grocery is normally distributed of a mean of 1,000 with a variance of 100. How many gallons must be in stock at the beginning of the day if Gillis is to have only a 5% chance of running out of milk by the end of the day? So he's trying to ensure that he really doesn't run out of milk. Like, that's a pretty low chance, and he's trying to make sure he can serve as many customers as possible. So first, start out by writing x is normally distributed 1,000, 100. So that's how we always write it, with that little squiggly or tilde. So now, based on like the data we've been given, we must find the quantity of milk that has to be in stock at the very beginning of the day. And this implies that 1 needs to find the value of x, that if I write it out, x is greater than or equal to x, like we normally do. And we need to have a 5% chance, or I guess that's 0.05. Sorry. Or p of x is less than or equal to x of 0.95. The second way I wrote it is always it's always easier because you're looking for the less than or equal to, or I just always find that it's easier. I don't know why, but we can find it. Also, we're trying to find it with the 95th percentile. So that was when I was talking percentiles above. We wouldn't look for the 5th percentile. We're looking for the 95th percentile because that's the actual demand at the grocery store. So if you remember, we're going to use the norm inverse formula from above, which is, and we have to have P, our mu, and our standard deviation. And so standard deviation is literally just the variance of our random variable. So that was 100, remember from up here? So just the square root of 100, which is 10. And then, so that means all we need to do is put this now into Excel. So our P is 95.95. Our mean, they gave that to us. We didn't need to compute. And then we found our standard deviation was 10. So I'm going to move on to the next setup of the other problem, and then we'll actually plug those into Excel. Okay, so the number of traffic incidents occurring in Bloomington in a single day has a mean and variance of 3. What is the probability that during a given year, 365 days, there will be at least 1,000 traffic accidents in Bloomington? So the big thing here is they're saying at least 1,000. So we just want to know what's the probability that we'll have 1,000 or more. So the random variable xi is going to be how we denote the number of traffic violations. I'm going to write that up here. So xi equals number of traffic accidents. And our I, or number of traffic accidents that would be occurring per day, because the I's are going to represent all of the days of the year. So it goes all the way to 365. And that means that, they also told us the mean and variance for all of our xi's are going to be 3. Okay. And so we're actually going to use the central limit theorem here, right? Because the central limit theorem, we use it for when we have an n sufficiently large. Our n goes from 1 all the way to 365. So instead of sitting here and summing up 365 probabilities times the mean, we would actually use this theorem. So basically, we're going to be looking for x equals x1 plus x2 plus ... x to 365. So it is sufficiently large, and we're going to closely approximate by a normal distribution for this random variable x hash mark. So all the hash mark ones are what we do with the central limit theorem. So I'm going to say central limit theorem right here. Okay. So the parameters would be, so the mean, all that would be is 365 times 3. Because they told us that the mean for a single day is 3. So we just multiply it by 365 and we'd get 1095. The same thing is going to happen for the var. So 365 times 3 gives us the same thing, 1095. So basically the standard deviation, again, is just that variance or mean under the radical. So 1095, I did this out ahead of time and found that it yielded 33.0908, best approximation. And so the probability that there would be at least 1,000 traffic accidents in Bloomington, we would denote it with P of x hash mark is greater than or equal to 1,000, right? Because this is showing that at least 1,000 is going to happen that day, but it could be more. So using our formula from above, I have x hash mark minus our mean all over the actual standard deviation is greater than or equal to 1,000, because we actually know the value for that, 1095, all over 33.0908. Okay, so now that we have our standardized normal variable, we can see, I did this all out ahead of time, but remember z is how we would denote the now new standard normal variable, and it's greater than or equal to negative 2.87. So I got negative 2.87 after calculating that out, and this whole thing right here actually became our z, because we don't know the value of x hash mark, because it's continuous and we have no idea like the actual amount of traffic accidents. So we'll just keep going with this. If I have something greater than or equal to, I can use our complement rule and actually do 1 minus the probability that z is equal to or less than or equal to negative 2.87. So if I use the complement rule, I can flip it and it makes our job a lot easier, right? Because I can rewrite this as the CDF of negative 2.87, which I can go look up in the table to find 1 minus 0.0021. And if I put that in my calculator, 0.9979 is the answer I got. So this is the required probability we just needed to set this up and use in Excel. I did this out to show you the central limit theorem, but we should get the same answer in Excel that we got for this problem. So you don't have to do all this work to set it up in Excel. I just wanted to have something to check our work with. If we put it in Excel, we would do 1 minus the norm dist formula. And again, right, we had 1,000 as our normal distribution because that's the amount of traffic accidents. So this is like our A. That's a bad A. So this is the A, and then we had 1095 as our standard as our mean, and then our standard deviation was the square root of that. And then we always put 1 here because that is what the formula stated. So I'm going to highlight this because this is very important. That's what we're going to go put in Excel. So stay tuned for the next clip. Okay, hey guys. So I just pulled up Excel. This is on my iPad, but you can use a computer. The function should work in anything like app, online, wherever. So right here, I'm just going to show you guys how you would go about doing this in Excel. It's super simple. So right here, this equals norm inverse. You always have to type equals in Excel to denote that it is a formula or a function you're trying to use. If not, it will just sit there. So norm inv, you see that? And you notice how it says probability, mean, standard deviation. So even if you forgot what goes where, it's kind of telling you. It says probability, but this is our pth percentile thing. So 0.95, our mean is 1,000, and our standard deviation is 10. So now, if you notice, I literally didn't even have to, it shows the formula up here, but it returned a value. So the answer to this problem is, I'm gonna write it in green so we remember, is 1016.45. Sorry, a little messy. Okay, so that's for that one. I'll go down to a new cell and type in what is highlighted in yellow. So we need to make sure that it matches the value we got using the central limit theorem. So 1 minus, again, you have to use your equals, either it will not register. Norm dist of 1,000, comma, 1095, comma, 33.0908, comma, 1. And it did return 0.99795. Okay, that's 0.99. Okay, so basically, my calculation on my calculator, I rounded a little bit off. So it's the same answer. It's correct. So this is the faster way to use it. If you don't want to do this anymore, you could always just plug these into Excel. And if you noticed, when I typed norm equals norm, there's like a million different distributions and things that you can use with the normal distribution in Excel. So just play around with it, get used to it, and thank you so much. Stay tuned for 12.7.